Hi, I hope Module 7 is going well. I wanted to respond to some questions that folks had about Module 7, Section 3, Question 5. So specifically, this is about a radioactive substance which is decaying exponentially. So a scientist begins with 100 milligrams of this radioactive substance. After 33 hours, 50 milligrams of the substance remains. How many milligrams will remain after 43 hours? So we're going to first need to solve for a constant using these initial conditions, and then we will solve again using what we found for our constant for the final condition. So we're going to use the exponential decay formula. Now this is written as a sub t equals a sub 0 e raised to the kt. And by sub, I mean subscript. So, for example, a sub 33 is the amount at 33 hours. And it's called sub because it's a subscript, whereas if it was a raised to the 33, that would be a superscript. So that's a subscript, and that's a superscript. So then we could also think of this as y equals a to the 0 e to the kt. But the subscript notation is more useful because it reminds us exactly what the a sub t means. So we'll start with 100 milligrams as our initial condition. Then we have e raised to the k and then if we had time t equals 0, this would just end up being e to the 0, which is 1, and we just have 100. So that's actually perfect, but it doesn't help you find k. And so instead what we're going to need to do is take the next part here, 33 hours and 50 milligrams. So we have a to the 30 sub 33 equals 100 e to the k times 33. We'll write that as 100 e to the 33k to make it a little simpler to work with. And then the amount at 33 hours, a sub 33, is just 50. Now you might look at this and wonder how we're going to approach it. So first we're going to look for something simple we can do. Since this is 100 times something, we can just think of this, we can just forget about this part here and just do 50 over 100 equals e to the 33k. And now we have 1/2 equals e to the 33k. Now here we need to get the 33k out of the exponent. And so what we're going to do is we're going to do something called taking the natural log of both sides. So we'll do ln of 1/2 equals ln of e raised to the 33k. Now you might ask what this part here even means. So when we have ln of something, that means log base e. And so log base e of e to the 33k means e raised to what power equals e raised to 33k, and that's just 33k. And so what's cool about that is that you can think of it as the log and the e canceling out, and we're left just with this. So now we have ln of 1/2 equals 33k, and we'll sit here and think about this. Oh, we can just divide by 33 on both sides, and now we found k, which is ln of 1/2 over 33. So let's now erase all this work and we're left just with k. So now we've got a sub t equals, remember the initial condition stays at 100. Then we have e raised to the ln of 1/2 over 33. Let's write that a little bit better. E raised to the ln 1/2 over 33 times t. And let's take a look at this in Desmos, which is a graphing calculator. You can also try this, follow along on your own graphing calculator. So we have Desmos. We've graphed 100 times e raised to the ln 0.5 over 33 times x. And so we see here at time t equals 0, we have the 100 milligrams. And at time t equals 33, we have 50 milligrams, so that's great. And now we want to know how many milligrams remain after 43 hours. So at this point, we could get an approximation by tracing the graph, which is 40.527. So let's write that down just up in the corner, and let's solve this algebraically to see if we get the same answer. So here, this is pretty simple. It's the amount at 43 hours, a sub 43, and then we put 43. Remember that this is not an exponent, this 43. It's just being multiplied by this. So then I'm going to do this on the Windows calculator, but you'll probably be using a graphing calculator. And if you need help with the graphing calculator, just let me know, and I'm happy to help with that. So here we're going to start with this part with the exponent, and then we'll multiply it by 100. So we're going to go e raised to the power of double parenthesis 0.5 natural log divide by 33 close parenthesis times 43 close parenthesis equals, and then times 100. And that gives us 40.527, which is the same answer we got tracing the graph. So that's great because it means a sub 43 equals, and then it's said to round it to 1 decimal place in the problem, so 40.5 milligrams. Now I just wanted to give a little bit of comment about the number e. So the number e is really interesting because it is what's called an irrational number, which means that it has as many decimal places as you want to calculate for it. So we're going to have, so we could look up, for example, 1,000 digits of E, and we'll see that we have 2.718281828, and this goes on essentially forever, and we could prove that it goes on forever, but I'm not going to do that here because we can only have a maximum 15-minute recording. And we also could do... Oh, and then the other thing I wanted to show you is that, so E is an irrational number, and a lot of people think that that means that it's crazy, insane, or doesn't make sense, but that's not actually true. What irrational means is it cannot be written as a ratio of integers, meaning we couldn't do 10 over 3, for example, or 1050 over 4 and get E. That's not going to happen. It's also what's known as a transcendental number. And what that means is that it is not algebraic, meaning you could never write a polynomial and solve and get E. That'll never happen. And so that's why it's called a transcendental number. And it's actually one of my favorite numbers. And if you continue on in mathematics, you'll learn a lot more about it. And so I'm hoping that just playing with it a little bit here, you'll get a little bit of an appreciation for it. And just know that if you continue on further in your studies, you'll learn even more about it, and it will turn out to be one of the most important numbers you'll ever see. So that's kind of neat. And so just for a quick review, the way we solved this problem was we started by taking 100 and plugging in for a sub 0, and then taking 33 hours and putting that in for t, and then 50 milligrams and putting that in for a sub 33. We solved for k. Then we wrote the new formula, which is the one that we graphed in Desmos. Make sure this isn't an exponent. And then we put in 43. We found a sub 43, and that was our answer. Alright, thank you for watching this video, and please reach out if you have any questions. Talk to you all soon.